Start. Hello friends. Friends, if you remember our module 1, in that already we had discussed about the stress strain relationships, engineering constants, 5 strength parameters, unidirectional laminas, and lastly we had discussed about 9 elastic constants. These 9 elastic constants can be found experimentally by conducting a series of tensile, compression, shear test on unidirectional lamina and obviously on the laminates. You should also remember about the discussion which we had about the isotropic materials, their experimental evaluation with regards to the calculation of different parameters like fiber volume fraction, packing geometry, processing, and many more individual constituents. Also, we had discussed about the elastic constant terms, stiffnesses, strengths, also some individual constituents. Now in the module 2 we will have to discuss about the micromechanical analysis of a lamina. Though we have already discussed in last 3 or 4 lectures about the same, but I am going to take a review of the same with certain objectives. The objectives we can define like we have to develop a concept in between the volume, weight fraction, and the volume of fibers, volume of matrix, density of different materials, and obviously we have to take void fractions into considerations in the fabrication of a composite. Find the 9 mechanical and 4 hygrothermal constant is also our motto, which we have to solve in this same module. 4 elastic moduli, 5 strength parameters, and 2 coefficients of thermal expansions. Though we are not much more concerned with the thermal expansion, coefficients of thermal expansion, but these 2 also one has to consider in order to design a perfect composite. And these all composites are to be calculated for a unidirectional lamina from their individual properties of fiber and the matrix, fiber volume fraction, and fiber packing. And also finally we have to discuss about the experimental characterization of these 9 mechanical and, if required, the hygrothermal constants. Now we will discuss about the different type of laminas, a different type in the sense non-homogeneous laminas and the homogeneous laminas. In this discussion, we have to take 2 points into consideration, which are the main points in order to calculate the different parameters to establish the relationship between the micro and the macro laminas. These points are as follows. A unidirectional lamina is not homogeneous. This is a uniform statement which we have to keep in our mind always. However, we can assume that lamina can be a homogeneous by taking its average response. If you remember, we had already discussed in our module 1, we had taken the average responses of stresses and the strains in order to calculate the different loads as far as the mechanical loads are concerned, or the hygrothermal loads are also concerned. We have not considered the hygrothermal in module 1. The second important point in order to distinguish between non-homogeneous and the homogeneous lamina is the lamina is simply looked at as a material whose properties are different in various directions. Once again, I am repeating the same, whose properties are different in various directions, but not different from one location to another location. It means a lamina will be considered as homogeneous lamina only when its properties are different in directions, but they will not differ location wise. It means from one location to another location. Now we'll discuss about the volume and mass fractions, density and the void content. These all points are necessary from experimental point of view. And the formula for the fiber volume fraction will be defined as Vf by Vc. A small Vf by Vc. I must mention a small Vf by Vc. A small Vf is volume of fiber. A small Vc is volume of composite. Here I want to mention capital V with subscript R for fiber volume fraction. It means for volume fractions, and small letters with subscripts R for the volume. Like Vf is, small Vf is volume of composite, volume of fiber, and small Vc is volume of composite, and similarly the small Vm is volume of matrix. Similarly, we can define the matrix volume fraction as the ratio of volume of matrix and the volume of composite. And after that, this we had already discussed that the sum of volume fractions, it means the fiber volume fraction and the matrix volume fraction must be unity. And from equation 2.1, which we had discussed, 2.1 in the sense 2.1 you can see the PDF which I had already uploaded. Then Vf plus Vm equals to Vc. Small Vf plus small Vm equals to Vc. It means volume of composite is the sum of volume of fiber and the volume of matrix. Similarly, we can define the mass fraction ratios. For example, capital Wf, it means weight fraction, which is the ratio of weight of fiber to the weight of composite. Similarly, we can say the same about the volume fraction of matrix, which is the ratio of Wm to the Wc. As we had discussed in the previous slide or with the previous formulas, once again the sum of mass fractions must be unity. For example, Wf, capital Wf plus capital Wm equals to 1. And finally, with the help of above equation, the sum of small Wf plus small Wm equals to small Wc. It means fiber weight plus matrix weight equals to the weight of the composite. From the definition of the density of a single material, we can correlate these two, as these two does mean Wc and VC, as WC equals to rho CVC, and similarly WF equals to rho FVF, and WM equals to rho MVM, and finally, which we had already discussed, that constitutes or the sum of WF plus WM equals to WC. Now, with the help of above equations, which we had discussed in the previous slide, the mass fractions and the volume fractions can be correlated as capital WF equals to rho F by rho C into capital VF. Similarly, we can define the weight fraction for matrix in the ratio of rho M by rho C into capital VM. Now, in terms of individual constituent properties, the mass fractions and volume fractions can be correlated as capital WF equals to rho F by rho M divided by rho F by rho M capital VF plus VM, and the whole multiplied by VF. And similarly, for matrix weight fraction, we may define as 1 divided by rho F by rho M and 1 minus Vm. It means capital VM has been replaced by 1 minus Vm and plus Vm, and the whole multiplied by Vm. Hence, from the above discussion, one can conclude that we should always state the basis of calculating the fiber content of a composite in terms of mass or volume. What does it mean? If let us suppose we are discussing other things experimentally, it does mean we have to take the fiber content always in terms of mass, either in mass or in volume. So based on the above equations, it is evident that volume and mass fractions are not equal, and that the mismatch between the mass and volume fractions increases as the ratio between the density of fiber and matrix differs from 1. Again, I am repeating, the mismatch between the mass and volume fractions increases as the ratio between the density of fiber and matrix differs from 1. As we had discussed in the previous slides, in the similar fashion, we can derive the formulas for density. And this is as follows: rho C VC equals to rho F VF plus rho M VM. And again, rho C equals to rho F and VF by VC, and plus rho M VM by VC. Now we can use the definitions which we had already discussed in our previous slides between the fiber and the matrix volume fractions. For example, small VF by VC equals to capital VF, and similarly small VM divided by small VC equals to capital VM, and that constitutes the equation 2.8, which I am mentioning here. I am mentioning the equation numbers. You can refer the PDF file which I had already uploaded. Then finally this equation becomes rho C equals to rho F capital VF plus rho M capital VM. And finally, the density of composite in terms of mass fractions can be found with the following formula: 1 over rho C equals to capital WF divided by rho F plus capital WM divided by rho M. This formula we can use in order to calculate the density of overall composite. So with the help of previous discussions, we have to solve one example. And this example is based on glass fiber. It means the fiber is made up of glass and the matrix part is of epoxy, and both of this fiber and the epoxy constitute a lamina. In this one thing I want to put emphasis that we have used 70% of fiber volume fraction, and this 70% of fiber volume fraction we have kept constant in all the examples which we are going to solve in this particular module. And for the different properties of this glass and epoxy, we have to use the tables which I will discuss in the next slides. And with the help of these tables, we have to identify the density of the lamina, mass fractions of both the constituents, fiber and the epoxy, and the volume of composite lamina for a mass of 4 kilograms, and last volume and mass of glass and epoxy as we have used in part C. This table 2.1 has the typical properties of fibers, dedicatedly made for fibers, and the mechanical properties of fibers I had included in that, like axial modulus, transverse modulus, and so on and so forth. And similarly, the different tensile strengths like axial, like transverse, and shear strength, and the last property, which is very important, specific gravity. And similarly, this table number 2.2 is dedicatedly made for the properties of matrices, and the same properties as we had discussed for the fiber has been listed for the matrices, like axial modulus and the Poisson ratio, different type of Poisson ratio, coefficient of thermal expansions, and the shear strength in various modes like tensile, compressive, and shear. Here we can see the burn test to be performed for an identification of volume fraction of carbon fiber. In this, we have to follow the ASTM standard number as 2584. This we have to keep in mind, ASTM standard 2584. In this, as you can see from the video, a horizontal oven has been provided to perform the burn test of a composite sample. The composite tabs are cut in the dimension 20 cross 20 mm, and then they will be put in a ceramic crucible for performing a burn test. Thereafter, burn samples of composites are to be taken out from oven and weighed to find their fiber volume fraction. So in this way, we can find out the fiber volume fraction with the help of burn test, which has to perform onto a complete composite or with onto the pieces of composite which of the dimensions 20 cross 20, and also depends on the capacity of oven. So in the previous slides, we had demonstrated about the carbon fiber extraction from the composite, and it will provide us the carbon fiber volume fraction. Now here is an important discussion about the same experimental aspect of the determination of fiber volume fraction from the constituents of composite. They are generally obtained by performing the burn or the acid digestion test, and these tests involves the density of specimen, which can be found by using the liquid displacement method, in which the sample has to be weighed in air first, and then the same sample with the same specification has to weighed in water, and the relative density of the composite can be calculated by the given formula, rho C equals to WC divided by WC minus WI, and the whole has been multiplied by the density of water. Now in the same context, the burning process of these composite samples varies from material to material. Here we are presenting some temperature based experimental analysis for some special composites especially used in structural applications. These are when the sample is dissolved in acid solution or to be burned. This process has to be used for the glass based composites. And when we use the carbon and aramid based composites, then these are to be digested in the solutions. Carbon and aramid based composites cannot be burned because carbon oxidizes in air above 300 degrees Celsius and the aramid fiber can decompose at high temperatures. Furthermore, we can discuss about the burning test to be performed on epoxy based composites. Now, epoxy based composites can be digested by nitric acid or a hot mixture of ethylene glycol and potassium hydroxide. These all tests you can perform in your labs also, because I had shown you the different type of composites in the sense I had shown you the carbon fiber based composites as well as the nano composites which were having the carbon nanotubes infused in that and the graphene infused in that, and you can perform easily burn test onto that in order to extract the carbon fiber from them. When digestion or burning is complete, the remaining fibers are to be washed and they are to be dried several times and finally they are to be weighed. The fiber and matrix weight fractions theoretically can be calculated by equation 2.2 as I had already mentioned. You can see my notes. The densities of the fiber and matrix are known to us. Finally, we can calculate the theoretical density of the composite, and the theoretical density of the composite can be easily compared with the experimental density of the composites. Now we'll solve the example which I had shown you in the, I think so, in this slide number 10, in which the only quantity is given to us, that was carbon fiber volume percentage, that was 70%. Now, in order to calculate this overall density of the composite, we must have the density of fiber and the density of matrix individually. But the quantity which is being given in the problem is only carbon fiber volume, glass fiber volume, that is 70%. Now, I would like to ask one question to you. How will calculate this rho f and rho m? I am giving you one clue that we can calculate this from the table number 2.1 or the 2.2. Now similarly we can calculate the capital WF. It means the fiber volume, weight volume fraction of fiber and the weight volume and the weight fraction of matrix, and the sum of these two, WF and WM. And obviously this must become as a unity in order to verify the weight of the composite. And now onwards we can calculate the volume of composite, and that is the ratio of WC over rho C, and here we can calculate. And now VF equals to capital VF into small VC. It means capital VF is the ratio of small vf divided by small vc, and we may have the value of the fiber volume vf. Similarly, matrix volume fraction capital Vm is the ratio of small vm to the small vc, it means matrix volume to the composite volume, and we may calculate. Now we can calculate the weight of the matrix as the product of the density of the matrix and the volume of the matrix, that is rho m a vm, and here it is. Now weight fraction or wf, small wf, will be calculated as the product of rho f and vf. Now in the coming discussion, we will emphasis on the void content of a composite. During the manufacturing of a composite, voids are introduced in the composite, as you can see in the figures or in this current slide. This causes the theoretical density of the composite to be higher than the actual density. I must repeat this sentence because this is the important one. This causes, it means the presence of voids causes the theoretical density of the composite to be higher than the actual density. Also, the void content of a composite is determinantal to its mechanical properties. These determinantal properties must include shear strength and stiffnesses, compressive strengths, transverse tensile strengths, fatigue resistance, moisture resistance. Also, we will have to discuss one more thing over here itself. A decrease of 2 to 10% in the preceding matrix dominated properties generally takes place with every 1% increase in the void content. I must repeat this sentence because this is the important one, which tells us about the different percentages of the void content. A decrease of 2 to 10% in the preceding matrix dominated properties generally takes place with every 1% increase in the void content. And now onwards we will see how the void content will be formulated in the form of different weights and densities. Now we can see through this SEM image, SEM scanning electron microscopy image of a carbon fiber reinforced epoxy composite. Here we have drawn one hexagonal over here. Hexagonal does mean, it means circle to circle we have joined and made a hexagon. And this I had already discussed in my previous class that it is a representative volume element actually. Representative volume element is used to convert the non-homogeneity of a composite into the homogeneity of a composite. And as this we had already discussed in our previous talks. And the empty space which is showing nearby to these cylindrical fibers is due to the void content and with epoxy. Now in this slide, four SEM images of carbon reinforced epoxy composite have been displayed, and from these SEM images, further we have calculated the effective moduli of a continuous fiber reinforced lamina. If we see the figure number A, in that cracks propagation have been shown, and these cracks were propagated in between the fiber and the epoxy. And these cracks were oftenly propagate because of the void contents. In the figure B, in SEM image B, matrix debonding is there. Matrix debonding is due to fiber pullout. So these two micromechanical analysis are there. One is the crack propagation, and that is because of the void content, and in the figure B or SEM image B, matrix debonding and the fiber pullout is there. And in SEM image C, matrix debonding and fiber pullout is there. Adhesive fracture is there. Adhesive fracture does mean epoxy fracture is happening over here. And the last one is dedicatedly made for the rough and serrated failure surfaces. It means the surface of the carbon fiber. So if we conclude these SEM images of carbon reinforced epoxy composite, there are several cracks propagation are there, and these cracks propagation is because of the void contents, and void contents. Due to void contents, there may be occurrence of debonding in both the forms. Matrix can be debond or the fiber can pull out. And similarly, the fracture because of epoxy and the rough surfaces. So likewise, these SEM images can be explained. These are the few SEM images once again dedicatedly made for effective moduli of continuous fiber reinforced lamina. In this we had shown the fracture occurs in the carbon fiber surface. So it is very much clear from all the SEM images that fiber pullout is there, or the fracture occurs because of certain factors like debonding, like adhesive debonding, and the contaminated epoxy.